In this video, we'll talk about the mean value theorem. Let's start off with just the general idea. And the general idea of the mean value theorem is that for certain functions, which happen to be both continuous and differentiable over an interval, if we look at the secant segment that joins 2 points, the mean value theorem guarantees that there must be a point somewhere along the way where the tangent line is parallel to that secant line. So here's just a rough eyeball sketch of what we're talking about. And the idea there really is to say that the slope between these 2 points must be actually achieved at some point. The slope of the curve at the point is equal to the slope between 2 points. So we'll take a little bit of time to formalize this, but here's essentially the gist of it. Let's start with the conditions. We're going to suppose our function f is continuous, and remember that we define continuity on closed intervals, and differentiable, we define differentiability on an open interval. And if you think about it, a lot of the functions that we're interested in have those 2 conditions. This drawing represents a 1. For the sake of our diagram, let's go ahead and let point A, or rather value A, be here, and value B be there, and that would indicate essentially these 2 points on the curve. Here's the conclusion of the theorem. Then there must exist a number C. C is inside the open interval AB, and this condition is true. F prime of C, remember that's the slope of the curve at a particular point, is equal to f of B minus f of A all over B minus A. So this is the symbolic expression that says the slope at one point is equal to the slope between the 2 points. So if we come back to our thought earlier of constructing the segment between those 2 points, then the slope of that segment is given by this difference quotient. And if we were to find that one point where the tangent line to the curve runs parallel to the slope between those 2 points, then C is a reference to the input value that this theorem guarantees must exist in the interval between A and B, where that slope is found. It could happen more than once, but this theorem guarantees that it must happen at least one point. So let's go ahead and take a look at a couple of examples. Oops, here's the same diagram. In example 1, we're starting off with an idea that we have a function that's defined, and even before we get to the idea of applying the mean value theorem, we really need to check the conditions. Is the function continuous, and is it differentiable? And since this particular function is a polynomial, it's continuous for all real numbers, and it's differentiable for all real numbers, which means it's continuous and differentiable on both interval 0, 3 and interval -1, 4. So we can apply the mean value theorem. And in this case, since it's continuous and differentiable, we know there is a C where f prime of C is equal to, and now we're going to use that difference quotient formula. I'm just going to do some of that side work right here. F of B would be f of 3. F of A would be f of 0 over 3 minus 0. And if we calculate these values, f of 3 would be 14. F of 0 is 5 over 3, and that simplifies to 3. So there's the application of the mean value theorem. There must be a number C. C is somewhere between 0 and 3 with this condition. I'll just annotate that right here. 0 less than c less than 3. So all that's changing in part B is we're applying it to a new interval. And I'm going to write it a little bit differently this time. There is a c for which f prime of c is equal to f of 4 minus f of negative 1 over 4 minus negative 1. And in the same way, we'll just calculate these values. Let's say 4 squared plus 5 gives us 21. And negative 1 squared plus 5 gives us 6. 4 minus negative 1 is 5. And so simplifying that gives us that there must be a c where f prime of c is equal to 3. Now in this last example, that's just a coincidence that both times the slope would happen to be 3. That would change depending on the interval we picked, and it just so happens that those both gave us that calculation. It goes to show the process, though, that as long as our function is continuous and differentiable on an interval, we can apply the mean value theorem, which means there exists an f prime of c in that interval where that slope calculation must be attained. Let's look at a different kind of example now. In example 2, we have a function given, and we are supposed to find any values of c in the open interval 1, 3 that satisfy the mean value theorem. So let's start with a quick check of our conditions. We need to see that this function is continuous on the closed interval 1, 3 and differentiable on the open interval 1, 3. And what we can see from this function is x is not allowed to be 0. That's our only value that's not a domain value. But that means that for anything other than 0, this function is both continuous and differentiable. That means it's continuous on the interval 1, 3, and it's differentiable on the open interval 1, 3. So we can apply the mean value theorem. So now what we know is we need to talk about f prime of c. We also need to use the formula to find f of 1 and f of 3. And so f prime of c requires finding the derivative of this. We didn't do that in the last example because we weren't trying to find the values of c, but that means we need to literally solve the equation that we're setting up. So let's make a note that if f of x is x squared minus 1 over x, you can do the work to show that f prime of x, I'm just going to annotate this slightly differently, can be given by the formula 1 over 1 plus x squared. Pause the video if you want to verify that for yourself. And f prime of, or rather f of 1 plugs in and gives us a value of 0, and f of 3 gives us a value of 8/3. So let's start like we did in example 1 and apply the mean value theorem. There exists some value c where f prime of c equals f of 3 minus f of 1 over 3 minus 1. And now let's go ahead and substitute the parts. It doesn't really matter if I use f prime of c or f prime of x. I'm just going to leave it in terms of x. It's more or less the same. And plugging these in, I have 8/3 minus 0 over 2, and that's equal to 4/3. So the values of c that satisfy, are the values that satisfy this equation. I'm going to start by subtracting 1 from both sides. Subtracting 1 gives me 1/3. And then it just happens to be a fact that if 1 over x squared equals 1 over 3, then x squared must equal 3. And that gives us two solution values, x equals root 3 or x equals negative root 3. But before we get carried away, The mean value theorem is defined on an interval, and since we're looking at the interval from 1 to 3, we are going to ignore the solution that doesn't fall into that, and this is the value that's guaranteed. So the value of C for this problem that satisfies the conclusion of the mean value theorem is the square root of 3. Just for your information, the square root of 3 is about 1.7, and that definitely falls in this open interval.